Hello, welcome back to Algebra 1 with Miss Andrea. Today we're going to continue on in our statistics unit, which is module 8b, the second half. Online they're also calling it unit 6b, and this is going to be page 5 of that unit, which is known to us as lesson 5, and it's about interpreting and representing two variable data. So in the last lesson, we got to learn about linear regression, or finding the best fit line. So with a linear function, remember, it looks like a line when it's graphed, and it's in an f of x or y equals mx plus b format. This is your standard format, also known as your slope-intercept format, because m is your slope and b is your intercept. There's also a quadratic function in which your graph looks like a parabola. So you have a graph that looks kind of like a U, or it could be upside down and look like an arc. But either way, you have a place, a pivot point, a vertex in which the graph changes direction. So in this case, if it's opening upwards, the graph is going downwards. And then at the vertex, it's going to switch directions and move upwards. And same thing with it flipped in the other direction. If it were an arc, it would be headed upwards. And then at the vertex, it would change directions and head back down. So that's a quadratic function. An exponential function, remember, it has an asymptote where this graph is going to get closer and closer and closer and closer and closer to zero without ever actually touching the line. And the zero can change depending on if you add or subtract a number at the end of this equation. It usually crosses the y-axis, and it grows exponentially. It jumps every time you move this is exponential growth, so it's getting bigger. So every time your x gets bigger, your y will get increasingly bigger. So it may start out from going here to here, and then it'll jump up to here, to here, and then here. So you see it would get exponentially. Let me use my pen so you can see the growth. Say we started here, and then 1 is about there, 2 is about there, 3 is about there, and 4 is off the charts about there. 5 is going to be all the way past the top of my screen. So you can see for each equal spacing across the bottom here, the horizontal spacing, they're all equal. The vertical spacing is becoming greater and greater with each time our x increases by 1. So that's an exponential function, and it works the same way if it's exponential decay in that direction. It would be, though, as the x or the input values are getting smaller, the output values would increase exponentially. All right, so you need to be able to identify what these graphs look like, because when we place our data into a scatter plot, you need to see, okay, does that data all scattered about kind of follow the path of a line here? Okay, well, we could say that if I had all this data, it would follow the path of a line. If I had data that looked like this, and your data is usually not going to be in a single format. It's going to be, and you might have an outlier here and here, but your data will kind of still, you can look at it and say, well, that kind of looks like a parabola, or that looks like one of those swoops, the exponential functions, or I can see how those are all traveling in the same general direction. That's a straight line. So you need to be able to identify that in a visual aid, a visual way. Just look at it and see. So I've got some examples for us to look at to see if we can figure out which of these functions we should be looking for a best fit on. Here's one, and the main thing to notice on this one is this right here, the vertex. As you can see, it's going upwards towards the vertex, and then once it hits that, it starts going back down. So this is going to be a quadratic. Okay, you should already be very familiar with these. We've gone over all of these in the past. This one, it looks like it would be a straight line. Okay, so that one would be a linear regression. The first one was a quadratic regression. And then this one right here, you might think that this looks like it could possibly be a quadratic regression, because it's like, okay, well, that's half the parabola. But since we don't have the data going up on this side as well, then you cannot assume that this is going to be quadratic. If you don't have the change of direction clearly shown to you, then it's not quadratic. So this one is exponential. It's going to continue going down and down and down and getting closer and closer, but never actually touching the asymptote, wherever the asymptote is. Okay, so this one would have been a quadratic recession. So now, let's see. Oops. I have here a list of data points. Now, in the past, in previous units, we've looked at the data that we have and looked at the differences. Remember, if we have the same difference, a consistent or just the same difference between each of these pieces of data, when all this is ones, then we could say, oh, that's linear. But the second difference, if that's consistent, then that means it's quadratic. Or if we have a ratio instead of a difference, a consistent ratio, then that means it's exponential. Well, since this data does not actually hit what's graphed, you cannot use that identifying information to look at this data and see. You will never get a consistent difference or a consistent ratio or a consistent second difference, because the data points aren't actually on the line. So you won't get that. So the only way to really figure this out is to look, graph the points, look at the data, and see what shape it's looking like. So I went ahead and put these into Desmos, the online graphing calculator, so we could see all of these points and see what they looked like. So that's here. And as you can see, this is going to be a parabolic graph, because it's headed upwards and then it changes direction and heads downwards. So this one is definitely a quadratic. So what you have to do now is be able to find the best fit line for this. So we need the equation of the graph that's going to best fit this data, that all those points are going to be the closest to. So how do we do that? Well, we're going to use that metadata statistics calculator that we showed you before. And we're going to go to regression analysis, just like we did, and we're going to put in all of our data. So I've got that up here for you. I've already put it all in. But the one thing I want to make sure you note is that we chose quadratic this time. In previous lessons, we always chose linear. That's not what we're doing, because when we graph the data points, we saw quadratic. So we chose quadratic, okay? All the data is in there. We're going to hit analyze, and then you can see what pulls up. We have our regression equation here. Now, again, this is not in the proper format. For whatever reason, this calculator does not put it in standard form. Standard form would tell us that the variable with the highest exponent is going to go first. So your equation should actually read, and let's round to the nearest 10th, okay? If we round to the nearest 10th, this one would be 0.2. Let's round to the nearest hundredth, 0.24, and this one would be 1.06, and this one would be 0.01. So y equals 0.01, which is negative. Can't forget that negative right there, x squared. I'm going to mark that out because I've used it. And then I'm going to put this x next. It's a positive, so I'm going to put that there, 1.06x. And then my constant, which is 0.24. And since there's no sign in front of it, I know that that one is a positive 2, 0.24. So the proper quadratic regression equation is going to be y equals, or f of x equals negative 0.01 x squared plus 1.06x plus 0.24. All right, so now I want you to go ahead and pause the video, I want you to figure this out. You can plot these points by hand on some graphing paper, or you can use Desmos to plot these points. When you plot them, you do just like you would a line. In a line, you just type in y equals, and you type in the line information, right? Well, if you want to plot a single point, you just use a parentheses, comma, 0, parentheses, 0, comma, 20, close parentheses, and hit enter, and that's your first point. And then you enter the second point, etc., and so on. And so you're going to graph all these points, see what shape they are, and then you're going to go ahead and enter it into the metadata statistics calculator. Make sure you choose linear for linear, quadratic for quadratic, and one we haven't looked at yet, but you know is oh my gracious, the name escapes me all of a sudden. It starts with an E. Exponential. Exponential. Make sure you choose exponential. Let's go back and look at that real quick. Here. So we have linear, we have quadratic, you have cubic, and you have exponential. So if you have exponential, you choose that one. We are not going to deal with cubic, power, or logarithmic in Algebra 1. So you need to, after you plot the data and you input all of it here, choose linear, quadratic, or exponential before you choose analyze. Go ahead and pause the video and work on these numbers. Come back once you're done. All right, so here it is in Desmos. I've input all of these values into Desmos, and here's what we see. Now, it kind of looks like a straight line, but it's not. If you notice, each one of them seems to be further over to the right, and the differences between them seem to grow exponentially, right? And so if we were to continue to the left of 0, it would, the differences, the vertical differences between these points would reduce exponentially until we started to see the curve down to the asymptote. So this is an exponential function. An exponential regression is what we're going to be looking for, a line to best fit this data. Because you can see from 0 to 1, we increase by 1, to 2, increase by 1. So all of these horizontal increases are consistent, but you can see that these output differences definitely grow exponentially. So this is an exponential function. So we put in all the data into the metadata calculator, and we chose exponential. Remember, we're under regression analysis, and then we choose analyze. And here is the formula that they spat out. Now remember, this is going to be, this one is actually in the proper format, but it's using this caret right here. So we're actually going to rewrite this and not use the caret. And we're going to round to the nearest, let's round to the nearest 10th. So we're going to have y equals 20.5 times, right there, that's a times. It looks like on the computer, it looks like a little star. So that's a times. So I'm just going to put a dot there. 1.92 is going to be 1.9. And that caret means to the power of x. Okay. So we have 20.5 times 1.9 to the power of x. And that's our final best fit exponential regression equation. All right, moving on. I've got one more for you to try on your own. Here's the set of data. Plot the points, see what shape you think it is, and then find the equation for me. All right, welcome back. I've gone ahead and plotted all the points in Desmos for us. And again, as you can see, as we move pretty evenly, just one place over each time to the right, the vertical differences in these do definitely grow exponentially. So this is, again, an exponential function, exponential regression. So we plug it all into our statistics calculator, make sure exponential is chosen. And then we have here the equation that's spat out. Let's round to the nearest 10th place. I wonder if did I copy the correct information? It says y equals 20.5. This feels like the exact same equation. Maybe I forgot to take a screenshot of the data for, or the information for our actual data here. So I apologize about that if that's what happened. 0.20, 1.9, 0.20. I don't see it on there. I may have not put in the correct data, so I apologize. But whatever this equation is on what you got should be just round to the nearest tenth and make sure you multiply it by the second number, round to the nearest tenth, and then it's going to be raised to the exponent of x. All right, now I believe you have a quiz coming up next. Go ahead and complete that quiz.